So, welcome back to another DSP class. Am I audible? Okay. In the previous class, we started our discussion on fast Fourier transforms. We understood the classification of computation of DFT and then discussed advantages of fast Fourier transform and started with decimation in time fast Fourier transform. Okay. We had derived two expressions which were x of k equals to f1 of k plus w n to the power k f2 of k. And one more equation was x of k plus n by 2 equals to f1 of k minus w8 to the power k f2 of k. And for both of these, k range was from 0 to n by 2 minus 1, only half the number of terms. Okay. Now these two equations combinedly give us one 8-point DFT. Okay, where f1 of k is one 4-point DFT, f2 of k is another 4-point DFT. These two 4-point DFTs are combined to give us one 8-point DFT. First 4 DFT points are given by the first expression, and second 4 or the last 4 DFT points are given by the second expression. Okay, and f1 of k is a 4-point DFT of the sequence f1 of n. Okay, or f1 of n's n-point DFT is f1 of k. Likewise, we have one more sequence f2 of n whose n-point DFT will be f2 of k. So f1 of k and f2 of k are DFTs of their respective time domain sequence f1 of n and f2 of n. Okay, but x of k and x of k plus n by 2 is a DFT of the sequence x of n. Then what is the relation between x of n and f1 of n and f2 of n? f1 of n will contain only the even numbered samples from x of n. So f1 of n will be defined with respect to x of n as x of 2n, meaning x of n point sequence will be divided into two n by 2 point sequences, out of which the first n by 2 point sequence will be having only even numbered samples from the original sequence x of n, and f2 of n will contain only odd numbered samples, which will be represented by x of 2n plus 1. Odd numbered samples will be represented by the second sequence f2 of n, and their respective n by 2 point DFTs will be f1 of k and f2 of k, and these two n by 2 point DFTs will be used or combined to obtain one n point DFT represented by x of k and x of k plus n by 2. Did you all understand this equation? Did you all understand this concept, whatever I did explain now? Are you all familiar with all the notations here? X of n will be one n point sequence, will be dividing it into two n by 2 point sequences, f1 of n and f2 of n. f1 of n will be containing only even numbered samples from x of n. f2 of n will be having only odd numbered samples from x of n. Their n by 2 point DFTs will be f1 of k and f2 of k. Will be combining these n by 2 point DFTs to obtain one n point DFT, which is the decimation in time fast Fourier transform. Now, these two sequences are to be further decomposed, but I hope all are following the concepts and the notations that we are using. Okay, but before we continue any further, let us consider a specific example. Now, let us develop this decimation in time fast Fourier transform for specific value of capital N, and let's consider capital N is equal to 8. If capital N is equal to 8, the discrete time sequence x of n will be having 8 samples, x of 0, which is the first sample. Now this is a discrete time sequence. Because we are generalizing, I am taking these notations: x of 0, x of 1, x of 2, 3, 4, 5, 6, and 7. For capital N equals to 8, discrete time sequence will be having 8 samples starting from x of 0 through x of 7. Okay. Now from this, how do we obtain two n by 2 point sequences? F1 of n and F2 of n. F1 of n will be taking only even number samples represented by x of 2n. Okay. Now x of 2n, the range of small n here, the range of small n will be between 0 to n by 2 minus 1. It will be between 0 to n by 2 minus 1. Capital N is 8, so 8 by 2, 4 minus 1, 3. Okay. Now, which are the even numbered samples and which are the odd numbered samples from this discrete time sequence? Now, for that, you can identify them by the index, or you can substitute n equals to 0 to 3 in this x of 2n. For n equals to 0, x of 2 into 0 will be 0. So, x of 0 is one of the even numbered sample. Next, for n equals to 1, x of 2 into 1, x of 2 is the second even numbered sample from this sequence. And likewise, for n equals to 2, 2 into 2, 4, x of 4. And likewise, x of 6. X of 0, x of 2, x of 4 and x of 6 are the even numbered samples from this discrete time sequence by the virtue of their position as well as for different values of n. Okay. And F2 of n, which will be containing only odd numbered samples, is represented by x of 2n plus 1. So again substitute n equals to 0 to 3 in this expression. For n equals to 0, 2 into 0 will be 0 plus 1. So x of 1 will be the first odd numbered sample. Next, for n equals to 1, 2 plus 1, 3. X of 3 will be the second odd numbered sample in the sequence. And likewise, the remaining 2 will be x of 5 and the last one x of 7. So, F1 of n, which contains only even numbered samples, are x of 0, x of 2, x of 4, x of 6. F2 of n, which contain only odd numbered samples, are x1, x of 1, x of 3, x of 5, and x of 7. And these two, F1 of k and F2 of k, are the 4-point DFTs of these two sequences. 4-point DFTs of these two sequences. Are you all following?
Yes, sir.
Okay. Now let us write these expressions. Okay. We had written these expressions in the previous class. Now let us develop these equations for n equals to 8. For the example that we have considered now. For n equals to 8, what will be the range of k? How many values k will be having? The range of k is from 0 to n by 2 minus 1. N value is 8, so it will be from 0 to 3. Or k will be taking 4 values. K equals to 0, 1, 2, and 3. Okay. Now substitute k equals to 0 in the first equation. For k equals to 0 in the first equation, it will give us x of 0, which is the first DFT point, which will be obtained for k equals to 0 in the first equation. We get f1 of 0 plus capital N is 8, so W8 k is 0 multiplied by f2 of 0. Multiplied by f2 of 0. So first DFT point x of 0 will be sum of the first DFT point in f1 of k and f2 of k, but multiplied by the square factor W80 to the second DFT point. Okay. If you substitute k equals to 0 in the second equation, what will it give us? and write one below as well. X of 0 will be f1 of 0 plus w8 0 f2 of 0. Okay. Now we'll get this equation when we substitute k equals to 0 in the first equation. Now substitute k equals to 0 in the second equation. It will give us, now k is 0, n by 2. N by 2 is 4. 0 plus 4, 4. So for k equals to 0, second equation will give us fifth DFT point, which will be represented by x of 4, which will be difference of still k is 0. We have substituted k equals to 0 in the second equation. Okay, so it will be f1 of 0 minus w8 0 multiplied by f2 of 0. So first DFT point obtained by first equation will be sum of the two DFT points, but second DFT point will be multiplied by this twiddle factor. The second or the fifth DFT point will be difference between the two DFT points in the n by 2 DFT sequences, but this twiddle factor will be multiplied to the second DFT point. And likewise, if you substitute k equals to 1 in the first equation, you will get x of 1. X of 1 will be equals to f1 of 1 plus w8 1 multiplied by f2 of 1. And for k equals to 1, second equation will give us 1 plus 4, 5, x of 5, sixth DFT point equals to f1 of 1 minus w8 1 f2 of 1. And likewise for the remaining two values of k. For k equals to 2, first equation will give us x of 2, which will be f1 of 2 plus w8 2 f2 of 2. And the second equation will give us x of 6, which will be f1 of 2 minus w8 2 f2 of 2. For k equals to 3, first equation will give us x of k, which will be f1 of 3 plus w8 3 f2 of 3. And the second equation for k equals to 3 will give us 3 plus 4, 7, x of 7, the last DFT point. X of 7 will be f1 of 3 minus w8 3 f2 of 3. Okay. Now in this order, whatever these equations have been written, now in this order, two n by 2 point DFTs will be combined to give us one 8 point DFT. Okay. Now let us represent this. Let us represent these equations, what they are written, in terms of a signal flow path. Okay. Now you can look at these equations as the transformation from input to output. Input at this stage are two 4-point DFTs and output is one 8-point DFT. Okay. So let us represent the output. Let's say x of 0, x of 1, x of 2, x of 3, 4, 5, 6 and 7. The output has to be 8-point DFT, which will be obtained by combining two 4-point DFTs, f1 of k and f2 of k. So if this is the output at this stage, input has to be two 4-point DFTs, f1 of 0, f1 of 1, f1 of 2 and f1 of 3. Okay. Next, this is one 4-point DFT, f1 of k. This is f1 of k. Next, f2 of 0, f2 of 1, f2 of 2 and f2 of 3. This is the second input, which is the second n by 2 point DFT, f2 of k. Now, according to these equations, according to these equations, how these two 4-point DFTs is this visible? Okay. Is this visible? Okay. Now, how inputs at this stage are being transformed to the output, okay, which are the 8-point DFTs. Now, to obtain x of 0, we are adding f1 of 0 and f2 of 0. f1 of 0, one of the signal is here itself, f1 of 0. But to obtain this x of 0 point, I need f2 of 0 as well. f2 of 0 is here, so I'll make one connection. So to calculate this point, x of 0, I'll be requiring two signals. f1 of 0, which I have made the connection earlier. I have made another connection from f2 of 0 now. Okay, but the second point, f2 of 0, has to be multiplied by w8 0. So for at this point, f2 of 0, I'll be multiplying w8 0. Is this okay?
Yes, sir.
Okay. Next equation is x of 4. That is this DFT point. Now to obtain this DFT point, what two DFT points are required? f1 of 0 and f2 of 0. Already f2 of 0 point has been established here. I have drawn it previously. But I need f1 of 0 as well. So I will make a connection. f1 of 0. Okay. But what is the operation between these two? The first equation was addition. So we had drawn the line directly. But here I need to subtract. Okay. So to have that subtraction, will multiply -1 at the other end, only to the bottom points. Are you all following this? Are you all following this?
Yes, sir.
Okay. From the next two equations, x of 1 is obtained by f1 of 1 and f2 of 1. Okay, already f1 of 1 is established here, so we'll have to take f2 of 1, which is here. But f2 of 1, w8 1 is multiplied, so we'll multiply w8 1 towards the left side. Okay, and for x of 5, the same 2 points are to be subtracted. That is f1 of 1 minus w8 1 f2 of 1. Now to have that minus sign, will include -1. Okay. Likewise, for x of 2 will be f1 of 2 plus w2 multiplied by f2 of 2. And the same 2 points will give us x of 6. X of 6 will be f1 of 2 minus w8 f2 of 2. And last point, x of 3 will be f1 of 3 plus w8 multiplied by f2 of 3, and the last point, x of 7 will be f1 of 3 minus w8 multiplied by f2 of 3. Is this visible? Is this clear? Okay, so this is the last stage. Last stage. I had written the split the other day. 8, 4, 4, 2, 2, 2, 2. To calculate 8-point DFT by using decimation in time, to obtain one 8-point DFT, two 4-point DFTs are combined. Now this is how we combine two 4-point DFTs to obtain one 8-point DFT. This is the last stage. In its previous stage, how do we combine these four 2-point DFTs to obtain two 4-point DFTs? Have to be written. Are you all following? Yes? Okay, the same notes I have shared it today. Okay, if by chance board is not clearly visible, then you can refer to those notes. The same has been posted in the WhatsApp group today. Okay, now let's retain this. Okay. Let's retain this stage. Now to the previous stage, F1 of k and F2 of k will become the output. Now what will be the input to them? We'll look into that. Okay. Now that is the second stage of decimation. That is the second stage of decimation. Now we'll write the equations for those second stage of decimation. Okay. Now, in the second stage of decimation, now we have two sequences, F1 of n and F2 of n. Okay, which are n by 2 sequences compared to x of n. F1 of n has even numbered samples and F2 of n has odd numbered samples. Now, in the previous stage, in the second stage of decimation, these two sequences will be further decomposed. They will be further decimated into the number of samples will contain only the even numbered samples from F1 of n and odd numbered samples from F1 of n, and likewise even numbered samples from F2 of n and odd numbered samples from F2 of n. Okay. Now to understand that in a better way, let us write the sequence. F1 of n, which was represented as x of 2n, had x of 0, x of 1, x of x of 2, x of 4, and x of 6. Okay. Now let us decimate this n by 2 point sequence once again. Now let us call V11 of n. V11 of n is a subsequence of this decimation which contains only the even numbered samples. Which contains only the even numbered samples of F1 of n, and those even number of samples will be given by F1 of 2n. Or if we want to write this with respect to x of n, then it will be x of 4n. X of 4n. And for n equals to, what will be the range of n now? What shall be the range of n? What shall be the range of n for this? N will be from 0 to n by 4 minus 1, because we are decimating it further. Earlier it was n by 2 minus 1. Here, this 4-point sequence is again being divided into even numbered and odd numbered samples. So it will be n by 4 minus 1. Okay. And what are the even number samples from this F1 of n? Even numbered samples here are x of 0 and x of 4. We will be having only two samples here. X of 0 and x of 4 are the even numbered samples from F1 of n. Next, let's see V12 of n. The notation V12 of n containing odd numbered samples from F1 of n, which will be represented by x of 2n plus 1. X of F1 of 2n plus 1. F1 of 2n plus 1. Okay, are you all following? Now, if you want to write this with respect to x of n sequence, then it will be x of 4n plus 2. X of 4n plus 2. Now, if you substitute n equals to 0 and 1 in this equation, it will give us the odd number samples, and those odd number samples are x of 2 and x of 6. Okay, so from f1 of n, we obtained only even number of samples and denoted it by v11 of n, and v12 of n contain only the odd numbered samples from f1, which are x of 2 and x of 6. Likewise, we need to repeat this for the second sequence as well, f2 of n. f2 of n, which was x of 2n plus 1, which contained only the odd numbered samples, which were x of 1, x of 3, x of 5, and x of 7. From the original sequence x of n will again be decimated into even numbered samples and odd numbered samples. Okay. Now let's say v21 of n contain only the even numbered samples from the second sequence f2 of 2n. Even numbered samples here are, even numbered samples means the samples present at even index values. So those will be x of 0 and x of 1. And let's say v22 of n contain the samples, odd number samples from the sequence f2 of n, which will be represented by f2 of 2n plus 1. So which will be x of 3 and x of 7. X of 3 and x of 7. Okay. Now what did we do earlier? We had one 8-point sequence x of n. This 8-point sequence x of n was converted into two 4-point sequences, f1 of n and f2 of n, and their respective 4-point DFTs were obtained, which were f1 of k and f2 of k. These two were combined to give us one 8-point DFT. In the second stage of decimation, these two 4-point DFTs are decimated into four 2-point DFTs. V11 of n is one 2-point DFT. 2-point sequence. V12 of n is the second 2-point sequence. V21 of n and V22 of n, and those two are the third and fourth 2-point sequences. Now we need to take 2-point DFTs of these 2-point sequences and then combine them to obtain two 4-point DFTs. Are you all following?
Yes.
Okay. Now, according to the equations that we had written earlier, equations that we have written for x of k and x of k plus n by k. According to those equations, the 4-point DFTs f1 of k and f1 of k plus n by 4, and likewise f2 of k and f2 of k plus n by 4 will be given by v11 of k plus w n by 2 to the power k v12 of. Now these will be the equations. Okay, v12 of k. Likewise, f1 of k plus n by 4 will be v11 of k. The same equation, but instead of addition, will be subtraction. v12 of k. Now these two equations, where the range of k will be from 0 to n by 4 minus 1. 0 to n by 4 minus 1 will give us the first 4-point DFT f1 of k, just like we did here. And the next two, f2 of k, which will be given by v12 of k plus wn by 2 to the power of k, v22 of k and v21 of k minus wn by 2 to the power of k v22 of k. Now the range of k is also same here, n by 4 minus 1 to 0. Now these two equations will give us the second 4-point DFT F2 of k. Okay, and here v11 of k, v11 of k is the 4 DFT, n by 4-point DFT of the sequence v11 of k. Okay, earlier to this we had written 4 2-point sequences. Now these v11 of k, v12 of k, v21 of k, and v22 of k are the n by 4-point DFTs. In this case, 2-point DFTs of those sequences. v11 of n, v21 of n, v12 of n, and v22 of n. v21 of k, v12 of k, and v22 of k. These are the DFT pairs. These are the DFT pairs. Are you all following? Are you all following? Any doubts? Any questions? Any doubts? Any questions? Okay. Now, according to these 4 equations, okay. So according to these 4 equations, again, this is just like input-output transformation. Input are these 2 or 2-point DFTs. Input are these 4 2-point DFTs, and output are these 2 4-point DFTs. So in its previous block, this becomes the output now. In the first block, these were the inputs, and x of 0 to x of 7 were the output. Now in its previous block, f1 of k and f2 of k will become the output. Now what will be the input to them? So I will extend these lines. Okay? To represent the input-output relation. Okay. Is this visible? v11 of 0 is the first DFT point in 2-point DFT v11 of k. Okay? Likewise, v11 of 1 is the second DFT point in v11 of k. Likewise, v12 of 0, v12 of 1. Now these two are the 2-point DFTs represented by v12 of k. Next, v21 of 0 and v21 of 1. These two are the 2-point DFTs represented by v21 of k. And lastly, v22 of 0 and v22 of 1. These two are the 2-point DFTs represented by v22 of k. Okay. Now, according to this equation, now for both of these sets, k will be ranging from 0 to n by 4 minus 1. N was equal to 8, 8 by 4, 2, 2 minus 1, 1. So k will be having only 2 values, k will be taking only 2 values, k equals to 0 and k equals to 1. If you substitute k equals to 0 in the first equation, now you all work this out, okay? If you substitute k equals to 0 in the first equation, we will obtain f1 of 0. And from second equation, we will be obtaining f1 of 2. And those will be f1 of 0, f1 of 0 will be v11 of 0, okay, plus Wn by 2, n is 8, 8 divided by 2, 4. W4 to the power 0 multiplied by V W4 to the power 0 multiplied by V12 of 0. Now this will be the connection. Okay, and the second equation will give us F1 of 2. F1 of 2 will be V11 of 0. Okay, V11 of 0 multiplied by W40 with V12 of 0, but we have a minus sign. Because of that minus sign, will multiply minus 1. Now, why we are including minus 1 at this end itself means, if I include minus 1 towards the left side, then the first equation will also become subtraction. But first equation has to remain addition itself, but the second equation has to be subtraction. Now that subtraction will be included by multiplying minus 1 towards the right side itself. If we include it in the left side, then both the equations will become minus 1. Okay? Now, for k equals to 1, for k equals to 1 in the first two equations, the first equation will give us f1 of 1. So, f1 of 1, this point, will be v11 of 1 plus w41 multiplied by v12 of 1. And the second equation will give us f1 of 3, and f1 of 3 will be equals to v11 of 1 minus w41 into v12 of 1. Now this connection will be given by these two equations. And likewise, the second set of equations will give us the next 4-point DFT, f2 of k. f2 of 0 will be v21 of 0 plus w40 multiplied by v22 of 0. And f2 of 2 will be equals to v21 of 0 minus w40 multiplied by v22 of 0. Second equation will give us f2 of 2. Substituting k equals to 1 in both the equations. First equation will give us f2 of 1. f2 of 1 will be equals to v21 of 1 multiplied by w41 v22 of 1. And the second equation will give us f2 of 3, which will be v21 of 1 minus w41 into v22 of 1. Okay, so this is the second stage of decimation. In the second stage of decimation, 4 2-point DFTs will be combined to give us 2 4-point DFTs. And in the first stage of decimation, 2 4-point DFTs were combined to obtain 1 8-point DFT. Are you all following? Any doubts, any questions?
No, sir.
Okay. Now, and this continues for one more time. Okay, because these V11 of k, V12 of k, V21 of k, and V22 of k are the 2-point DFTs. Now, how to calculate those 2-point DFTs? Okay, now to calculate those 2-point DFTs, where DFT is defined as summation 0 to n minus 1 x of n w n to the power kn. Now it is like we need to calculate this 2-point DFT, and the outputs will be v11 of 0, v11 of 1. That is, now do not get confused between these notations. Okay, now these two are v11 of k, uppercase V, capital V, which are the output, and the input are small v11 of 0 and v11 of 1. Okay. Now, what are these sequences? In the second stage of decimation, we had written this V11 of N 2-point sequence had x of 0 and x of 4 in it. Okay. So V11 of 0 will be equal to x of 0 and V11 of 1 will be equal to x of 1. So basically, capital V11 of 0, 2-point DFT will be calculated from the samples from the sequence x of n itself. Because we are decimating them into smaller sections in stage by stage, we'll be using these notations to represent them. That's all. Okay. So using the DFT equation, now how do we calculate DFT? According to this equation, this V11 of K 4-point DFT or 2-point DFT, V11 of K will be summation n equals to 0 to n minus 1, lowercase V11 of n w into the power kn. Okay. Now we'll modify this equation. Now this is the standard equation. Okay. Now, where V11 of k represents 2-point DFT, V11 of n represents 2-point sequence. So what changes do I need to make? The range on n. There are only two samples. Two samples for n equals to 0 and for n equals to 1. Now let us expand this. And what will be the range of k for this? Range of k will also be having only two values because it is a 2-point DFT for k equals to 0 and for k equals to 1. Now if you substitute k equals to 0, you get V11 of 0. That is the first DFT point here. First DFT point. This will be given as V11 of 0 multiplied by W 2 to the power 0 plus V11 of 1 multiplied by W2 to the power W2 to the power, in this case n will be equals to 1 but k will be equals to 0. Still this will be equals to 0 itself. Is this okay? Okay. W2 to the power 0 will be equals to 1 because it's an exponential. So therefore, the first DFT point will be V11 of 0 plus V11 of 1. Are you all following this?
Yes, sir.
Okay. Now for k equals to 1 in this DFT, we get the second point in the 2-point DFT, which will be V11 of 1. What will it be? V11 of n or 0 W2 to the power. Now k is 1 but n is 0 here. So this will become 0 itself, first middle factor, but the second middle factor will be W2. Here both n is also 1 and k is also 1. So we will be having W2 to the power 1 multiplied by V11 of 1. V11 of 1. Okay. Is this okay? Is this okay?
Yes.
But what is W21? W2 to the power 1 can be represented as e to the power minus j 2 pi divided by 2. Because capital N is 2 here. So this will be e to the power minus j pi. And what is the value of e to the power minus j pi? It will be cos of pi will be minus 1. So this will be minus 1 always. So instead of W2 to the power 1 will include minus 1. Okay, or minus 1 multiplied by this V11 of 1. So this will be, second equation will be V11 of 0 minus V11 of 1. Okay. Now observe these two equations. How do they look? How do these equations look? They seem like x of k, the pattern of this C like x of k plus x of k plus n by 2, or f1 of k plus f1 of k plus n by 4. They look like the same, right? First equation will be addition, second equation will be subtraction. But the difference is we have not got any middle factor here. Now to include that middle factor, first these equations for to obtain 8-point DFT, we used 8-point middle factor values from 0 to 3. To obtain 4-point DFTs, we used 4-point middle factor values 0 and 1. Likewise, to obtain 2-point DFT, we'll have to use W20, W20. Now, what is the value of W20? W20 will be 1 itself. Now, to have the similarity of these equations or to resemble these equations in standard form, we'll be including these two factors. But including them will not make any change with the value. ಅರ್ಥ ಆಗ್ತಿದೆ? Are you all understanding?
Yes, sir.
Now these two equations are for V11 of k only, the first 2-point DFT. Now the same set of equations will be for V12 of k, V21 of k, and V22 of k. The only changes will be in these discrete time samples. Okay. Likewise, you follow this, will get that. So I'll represent them in terms of this signal flow graph. Now in the third stage of decimation, where we'll be calculating 2-point DFTs. Now those 2-point DFTs will be directly calculated from the input itself. Okay? Or to understand that in a better way, because they were decimated, this first sample will be V11 of 0. Is this visible? V11 of 0? Now is this visible?
Yes.
Now this is the first discrete time sample V11 of 0 in the first 2-point sequence. With respect to 4-point sequence, this will be represented by f1 of 0. For 4-point sequence, it was f1 of 0. In terms of the input sequence, this is x of 0. Okay, I'll write those notations here. Okay. V11 of 0, which is equal to f1 of 0. F1 of 0 is a 4-point sequence. In terms of 8-point sequence, its sample value is x of 0. Okay. Now V11 of 1. Now this is the relation of each sample with respect to 8-point sequence, 4-point sequence, and 2-point sequence. The notations used to represent these samples in the 8-point sequence. In terms of 4-point, this is f1 of 1, which will be equals to x of 4. Okay, for each stage of decimation, you converted 8-point sequence into half the sequence values. These represent that. V12 of 0 will be f1 of 2, which will be equals to x of 2. And like this. V12 of 1, f1 of 3, which will be x of 6. V21 of 0, f2 of 0, x of 1, V21 of 1, f2 of 1, x of 5. V22 of 0, f2 of 2, x of 3, and V22 of 1, the last sample, which will be f2 of 3, will be x of 7. Okay, so instead of writing all of them, I'll just use that with respect to the original sequence, x of First sample will be x of 0. Second sample will be x of 4. Third sample will be x of 2. Fourth sample will be x of 6. And likewise, x of 1, x of 5, x of 3, and x of 7. Okay. Now, we need to compute 2-point DFTs of this sequence and will be obtaining 2-point DFTs. These 2-point DFTs are combined to get 4-point DFTs, and these 4-point DFTs are combined to obtain 8-point DFT. That is the overall theme of this distribution in time fast Fourier transform. But according to the 2-point DFT equations that we had written earlier, the connections will be like this. B11 of 0 will be obtained by adding x of 0 and x of 4, but W20 will be multiplied at this point. And B11 of 1 will be obtained by subtracting x of 0 with x of 4, where x of 4 will be multiplied by this Query factor. And this is same for the remaining values. W20 minus 1, W20 minus 1, W20. Okay, is this visible? Is the complete signal flow graph visible? Okay, now this is how from the discrete time sequence will be obtaining n-point DFT in decimation in time fast Fourier transform DIT FFT algorithm. Understood? Understood? Any doubts, any questions? How did we obtain this signal flow graph? Yes? Yes or no? So the concept is very simple. From the given n-point discrete time sequence, that discrete time sequence will be successively decomposed to the smallest value that we can calculate the DFT here will be 2-point DFT. To calculate 2-point DFT, the n-point sequence will be divided into 2-point sequences. Those 2-point sequences are x of 0, x of 4 is one 2-point sequence. X of 2, x of 6 is another 2-point sequence. And likewise, x of 1, x of 5, and x of 3 and x of 7. For which 2-point DFTs will be calculated. These 2-point DFTs will be combined to obtain 4-point DFTs, and 4-point DFTs will be combined to obtain 8-point DFT. Now you can observe the nature of the input here. Now applying input instead in the sequential order x of 0, x of 1, x of 2, x of 3, the order, the index value of the input is different. It is shuffled. First we have x of 0, but the second sample instead of x of 1 we have x of 4. Next we have x of 2. Next we have x of 6. Now there is a reason why the input will be in the shuffled array form. It is called as shuffled array form. It has a specific reason for that. Now if the input will be in the shuffled array form, then the output will be in the normal order. But if the output is in the shuffled array form, input will be arranged in the normal order. Now we will go through all those unusual whatever we look at in the signal flow graph. But primarily, did you all understand how did we develop this? Okay. We'll discuss more on this signal flow graph. I will redraw this again in the next class, and we'll discuss more on this, but in the next class. Any doubts, any questions in today's class? Any doubts, any questions for today's class? Okay, if not, hold on, I will download the attendance.